A very good morning to everyone. Welcome to the second session of Talks at ENTC. This month, we have a very special guest joining us from Singapore. And we are proud to say that he is a proud alumni of the Department of Electronics and Telecommunication here at the University of Moratuwa. So without further ado, let us introduce our speaker today. For that, I invite Engineer Kitsiri Samarasinghe to give the introduction about our special guest today.
Very good morning to everyone. The Electronic Club organized this monthly series of talks inviting prominent Sri Lankan engineers, then scientists, researchers, and industry leaders. And the aim is to motivate the participants to draw inspiration for their future. Today we have the second session of the series. And on behalf of the Knowledge Hub of eClub, I warmly welcome all of you to this session. Today our guest speaker is Mr. Kalana De Silva. And let me introduce Mr. Kalana De Silva to you. Mr. Kalana De Silva graduated from Department of Electronics and Telecom Engineering of University of Moratuwa, our own department. And after completing his studies here as an undergraduate in 2014, he joined the industry as one of the founding members of the new, now renowned Parakum Technologies. Then in 2018, he went to Singapore for his postgraduate studies, and he obtained his Masters of Science in Engineering in the National University of Singapore. Then he obtained employment in one of the largest engineering firms in Singapore, the ST Engineering, where he joined the project team of Teleos satellite program. You may know Teleos means perfection in Greek. This program, Teleos, is a special program funded by the Singapore government, and he has now gained very valuable experience in the space satellite engineering for 2 years. So please join with me in warmly welcoming Mr. Kalana De Silva for this second session of the Talks at ENTC. And now I respectfully invite Mr. Kalana De Silva to share his valuable experience with us. Over to you, Kalana. Thank you.
Thank you, sir. It's been a long time since I've been in the department, so it's good to see all of you again after a long time. So today I was glad to accept the invitation by the eClub to deliver this talk to inspire and motivate our young engineers. So let me start my presentation, and I hope to make this an interactive presentation. So I would like to welcome all of you to raise your questions during the Q&A and engage in a very fruitful discussion. So I warmly welcome all of you, and thank you for giving me this opportunity. Okay. I hope everyone can see my screen right now. So
yes, Kalana, we can.
Okay, thank you, sir. Okay, so now I'm gonna guide you through a journey of exploring satellite design. So let me start off with a small self-introduction, but I think Kitsiri already gave quite a comprehensive introduction about myself. So I, of course, graduated from this very same department back in 2014. So it's been 7+ years now. And I obtained my master's in electrical and computer engineering from the National University of Singapore back in 2019. And as it was mentioned earlier, I was one of the founding members and also the former product manager of Parakum Technologies, where I worked for 4 years from 2014 to 2018. And currently, I'm a senior engineer of the Telios satellite program. I'm working for ST Engineering in Singapore. So let me briefly reminisce my days at Parakum Technologies. So I was, like I said, one of the founding members of Parakum Technologies, one of the 4 founding employees, which was formed under the patronage of Dr. Ajit Pasquale. So we had a shared vision when we established the company. We had a shared vision to uplift the electronics industry in Sri Lanka through a culture of excellence in innovation and entrepreneurship. So during those days, there was, I think now there's more electronics opportunities for the young undergraduates than we did back then. So back then there was a big gap for electronics graduates for core electronic jobs. So we wanted to do something to change that. And one of the ways we could do that is through a drive of entrepreneurship, a drive that is driven by innovation and entrepreneurship. So with this shared goal in mind, we established Parakum Technologies. So our final year project group consisted of myself and 3 others who were involved in developing a high efficiency video compression engine, hardware accelerated engine. And then based on that, we had some spin-off products and solutions which we took to the industry. And I am really happy to say that we were able to demonstrate a 4K real-time HEVC decoding on FPGA for the first time in published literature. That was back in 2014. And that paper, which we published in IEEE transactions on the circuits and systems for video technology, happened to win us the President's Award for scientific publication back in 2016. And then we also were involved in network traffic management products and solutions, which we built for enterprise and telecom operators. So these products are now deployed in several countries around the world. And Parakum Technologies continues to develop and deploy more products in this product line today. And of course, other than our own line of products, we were also engaged in multiple collaborations for US and European electronics and semiconductor companies. And we did various projects with them in terms of semiconductor IP development, chip design, and also electronic circuit design. So that's a brief cap of my days in Parakum Technologies. Of course, there was a lot of things which I can't go into details, but that's where I spent the first 4 of my years in the industry. Then going through my journey in Singapore, I entered the master's program at the National University of Singapore in July 2018. And I studied master's in electrical and computer engineering. And I graduated from NUS in June 2019. And right upon graduating, I joined ST Engineering Singapore. This ST Engineering is not the ST Microelectronics you might be familiar with. This is actually a Singaporean company. It's called Singapore Technologies Engineering, and it's one of the largest. It's the largest engineering company in Singapore, and they are involved in a lot of strategic development projects in partnership with the government. So our program, the Telios satellite program, is one such strategic development program, which is done under the patronage of the Singapore government as part of their strategic development goals to establish an independent space industry in Singapore. So I have been working here for the last 2.5 years as a senior engineer. And I've been specializing in the design and development of onboard electronics and computer systems for Earth observation satellites. So that's been my journey in Singapore so far. So moving on, I would now like to go into the satellite industry in general, and more importantly, where you could fit in the satellite industry as undergraduates. So as you are well aware, satellites form an integral part of our lives today. And the applications range from military and defense applications to a lot of consumer applications like broadband internet services. Satellites still form part of the global internet traffic, and also satellite communications could be satellite phones and broadcasting technologies, and of course navigation. Everybody uses GPS these days, from our phones to aeroplanes to shipping. Everybody relies on satellites for their day-to-day lives. So satellite applications cover a broad range of industries, and it is projected to grow significantly in the next decade, owing to some of the breakthrough technologies, which I will discuss later. So briefly touching on the satellite system design, I am not going to go into details of this because this is not the, it's going to take a lot of time if I go into details. So I'm just going to give you a systems level overview of satellites. So a typical satellite consists of a large number of subsystems. So there's a mechanical engineering part, there's also an electronics part, software part, and also aerospace engineering related part. So you could say a satellite team will consist of pretty much all the major disciplines of engineering. And as such, our team in the Teleo satellite program also consists of all these engineering disciplines, people who specialize in all these engineering disciplines. So the major components of the major subsystems of a satellite system are the power subsystem, the telecommand, telemetry, and control subsystems, the what we call the attitude determination and control subsystem, which determine the orientation and the orbit of the satellite. And then we have the propulsion subsystem, which give the satellite the ability to maneuver in space. And of course, its structure, which is a mechanical component of it, the static and dynamic parts of it. The thermal controls, as you are well aware, space is a vacuum, and we can't rely on any passive air cooling. So we need to have active thermal control in a satellite. Then, of course, we have the payload. The payload is what the satellite carries. It could be a communication payload for telecom satellites, or a camera, or a radar payload for Earth observation satellites. And the major part of electronics come in the TTC, telecommand, telemetry, and control, which forms the brain and the nervous system of a satellite, where you execute commands to control the satellite, you establish the ground communications with the ground stations, and how you communicate and send data to and from the satellite. So this is just a very brief overview. I just wanted to give you an idea of how broad the scope is and what are the components involved in building a satellite. So what you can see clearly here is that electronics play a central role in any part of the satellite. Any type of satellite, any type of application you take, electronics will play a central role. So there's plenty of opportunities for electronics engineers, good electronics engineers in this industry. So going on to satellite applications, I would like to briefly touch up on the types of orbits which satellites can have depending on their applications. So we would broadly categorize the types of orbits into three main categories. First is the low Earth orbit satellites, which are relatively close to Earth, starting from around 350 kilometers and going up to 1,000 kilometers, around the range of 1,000 kilometers. So most of the satellites, low Earth orbiting satellites, are in the 500 kilometer range. The International Space Station is somewhere around that range, and also the Starlink satellites and pretty much all other Earth observation satellites are within this range of low Earth orbiting satellites. Then we also have the medium Earth orbits, which range from 8,000 to 12,000 kilometers, which are also used for certain Earth orbits, which we call the geostationary Earth orbit, or GEO for short. which is around 36,000 kilometers high above the surface of the Earth. And this is mainly used for telecommunication satellites. So moving on to the types of satellites, what we have. So there are two major types of satellites. First one is Earth observation satellites. So Earth observation satellites are used for imaging and mapping the surface of the Earth. So also for remote sensing applications where you want to gather data, perhaps from the atmosphere or from the space itself, from deep space itself. So most of the time, these types of satellites carry optical and or SAR, or what we call radar payloads. So most Earth observation satellites will carry an optical, high resolution optical camera or infrared cameras, which can image the Earth. And some specialized applications will require radar payloads, which we call synthetic aperture radars, or SAR for short. So some satellites will carry both these payloads, whereas optical cameras have limitations when it comes to imaging under adverse weather or also under cloud cover. Optical cameras cannot see through the clouds and in bad weather. And also they cannot see through some of the obstructions like man-made obstructions. But when you have radar payloads using radar imaging technology, you can actually see in any weather condition, even under cloud cover, and sometimes even penetrate some of the man-made structures and acquire targets within these, that are hidden inside. So they are mostly used for surveillance purposes. And like I said earlier, pretty much all Earth observation satellites tend to be in the low Earth orbits because it's closer to the surface of the Earth. There's less scattering of the signals when you're observing Earth from close by. And also they have high revisit coverage when they're in the low Earth orbit. So this is a kind of a diagram showing the types of observation satellites available. So the one on the right-hand side is an SAR payload, which is why you have the dish antenna, which is part of the synthetic aperture radar. And then moving on, the next major type of satellites are the communication satellites. And these satellites, of course, are, as the name suggests, are used for telecommunication purposes. And they carry communication payloads, which can be RF communication, or in some cases, some special cases could be based on laser communications. And they are used for providing internet or satellite telephone or satellite TV broadcasting services. And traditionally, these, I say traditionally because there's a kind of a revolution which is happening in the satellite industry right now, which I will cover later. But traditionally, these satellites used to be operating in the geostationary Earth orbits, and they tend to use very large satellites, like several tons heavy satellites. The reason they use geostationary Earth orbits is because using geostationary Earth orbits, or as we call them, Clarke orbits, named under Sir Arthur C. Clarke, you are able to cover the entire Earth using a small number of satellites and create a global network, use a global network of satellite communications. But there are some disadvantages. Because of the big distance of the geostationary Earth orbit, there's a high latency involved. And because it takes a large amount of fuel to get to that orbit, the cost is relatively high to get to that orbit. So because of that, these satellites tend to be very costly, and they are only available in small numbers. So the amount of bandwidth that you can provide with these type of satellites is low. So they cannot support high-speed broadband internet with global coverage. So because of these reasons, what we call new space applications are actually starting to use lower Earth orbits, what we call LEO satellites, to provide telecommunication services. So I'll cover that in detail later on. So this is an image of a typical communication satellite. So as you can see on the right-hand side, these satellites tend to be very large compared to a human being. You can see just how big they are. And these satellites tend to be like 5-10 tons in weight and almost the size of a train carriage. So now that's that what I showed you earlier is what we call in the industry, we call it the old space industry, because that is that involves traditional development cycles and what we call more traditional customers, as we would say. But nowadays there's a new revolution happening in the space industry, and that's what we call the new space industry, and that involves a different set of stakeholders and a different mindset or different thinking. So one of the biggest applications for this new space is mega constellations of satellites, which involve tens of thousands of satellites in the low Earth orbit, which will provide communication, high bandwidth broadband internet communications. And not just using few satellites, unlike in the traditional constellations, these will use thousands or tens of thousands of satellites. So like I said, this is in quite the contrast to the existing geo communication satellite constellations. So to compare, this image that you see right now shows a typical mega constellation using the low Earth orbit. As you can see, the orbit is very close to Earth, and you have tens of thousands of satellites providing a near global coverage with a high revisit rate. And then on the other hand, on the right-hand side is, for comparison, I have shown a typical geostationary Earth orbiting satellite communication satellite constellation, which has relatively fewer satellites, and they are using higher Earth orbits. Of course, they can give global coverage, but due to the cost of launching satellites to such a higher orbit, you can't have that many satellites, and also you cannot provide. Because of that, you cannot provide high-speed broadband internet. So they are limited to certain applications, but most of the internet traffic, as you know today, flow through deep submarine cables and not through geo satellites. So when it comes to these mega constellations, like I said, the stakeholders are different. For traditional satellite operators, you have like a large satellite like Hughes Telecommunications, and also national level, government level operators. But when it comes to mega constellations, they are mostly driven by private enterprises. So SpaceX and OneWeb are the two leading companies who are leading the initiative, and SpaceX Starlink is the one who is actually developing the largest constellation. So the aim is to provide high bandwidth and low latency broadband internet with full global coverage. You can achieve low latency because unlike in geostationary Earth orbit, which has to cover a long distance, so the round trip latency is higher. But for low Earth orbit, where the Starlink would be somewhere around 500 kilometers from Earth, the round trip delay from the Earth to the satellite is very low. So you can have low latency broadband internet for even the most demanding applications. So for this application space, the focus is mainly on reducing the cost and achieving fast time to market. So unlike in traditional old space industry, where a lot of manual work and verification level is involved. For this type of mega constellations in the new space industry, you rely on fast manufacturing using assembly line type of production and high level of automation. And also you have a significantly reduced focus on component level reliability. In traditional space applications, I would say a satellite has as much reliability as an airplane, as a commercial airplane. And you know how reliable those things need to be. So, I mean, basically, when you go to buy components, you buy aerospace grade components. So aerospace means like for airline industry and the space industry, they're put together because they require the same level of reliability. So which means they literally, you cannot afford them to fail. But that's the traditional mindset where you rely on high availability using a small number of satellites. But in the new space industry, you want to reduce this focus on component level reliability and use commercial off the shelf components instead of aerospace grade components, except for some of the most critical parts of the satellites, so that you can produce them, mass produce them, and deploy them quickly. And the high availability is actually achieved by having a large number of satellites with a large number of redundant satellites in the constellation. So if you're sending 10,000 satellites into space, and you can afford to have several hundred redundant satellites, and even if one of them goes down, you have redundancy. So just like the global internet, even if several routers go down at a time, you still have redundant communication paths available. So you could afford to lose some and also have some downtime. Whereas in traditional geocommunication satellites, you would not be able to afford such downtime. So this is the this is the revolution that is happening, where the mindset is shifting from the traditional, high reliability aerospace grade components based design into more what we say reduced focus on component level reliability and having redundancy at the satellite level. And also to reduce costs, what we rely on is to have multiple satellites per launch. That means one rocket can carry up to hundreds of satellites, so that the launch costs can be reduced per satellite. Launch costs can be reduced, and you can share the launch services with multiple operators. And to do that, you need to fundamentally make the satellites different, so that they can actually so as you can see in this next image, so you can actually stack the satellites. Instead of having individual satellites in a payload fairing, you can actually stack them in a stored configuration. And once they're in space, they actually expand to get their final configuration. So this type of thinking is now driving the satellite industry into become a more streamlined, more assembly line based, and more standards oriented industry. So both Starlink and OneWeb currently have operational networks which they use for beta level testing, with Starlink having over 1,600 satellites in orbit as of 2021. And it's projected to grow significantly during the next decade. And both companies will launch over 10,000 satellites during this decade, and perhaps all the way up to 50,000 satellites if things go according to plan. And one of the other major breakthrough technologies that's enabling this kind of space applications is that the satellite launch costs are coming down due to the development of reusable rocket technologies. So the leader in this technology is SpaceX, of course, and they've taken the lead on developing reusable launch vehicles, which most parts of the rocket can actually land back safely on Earth and can be safely reused. And they have reused rockets for multiple missions, and this significantly reduces the entry barrier into space. And especially for low Earth orbits, for low Earth orbiting satellites, that's a major requirement. So I'm sure you would have heard about some of the exciting applications which are enabled by these kinds of high-speed broadband internet access using low Earth orbiting satellites. I'm not going to go through each and every one of them because that would simply take too much time. But if you are interested, of course, you can read up on these potential applications which Starlink is aiming to provide through this. And one of the major defining factors of that I need to highlight is that there is no major vendor who has in the current industry, there is no single vendor who has global coverage, truly global coverage for high-speed broadband internet access across the world. So if this succeeds, companies like Starlink and OneWeb will have a truly global network where they can provide broadband internet services to anywhere in the world. So anybody with a Starlink connection can travel anywhere in the world and access their services without any restrictions, without any geographical restrictions. So these is the kind of applications that are opening up for the new space industry. So coming back, so like I said, when we look at the nature of the industry, we have this old space versus the new space. So let me try to compare the two industries and how they vary. So old space industry used to be driven by national governments and their related subsidiary organizations like NASA and of course ESA, the European Space Union Association, and also the Russian and Japanese, Korean, and also Chinese. You could say they have their own national level organized space organizations, and also there's there are also some big multinational companies which were available in this traditional old space industry, but the number of stakeholders are still relatively low. But in the new space industry, this is mostly driven by commercial, public, and private companies with mostly private investments like venture capital investments, and they operate with different strategies and with different objectives. In the old space industry, they were mostly serving strategic objectives of nations and were most often not profit oriented. Whereas in the new space industry, they are serving commercial objectives and they want to get close to consumers, like as close as possible to consumers, and provide consumer service level services. And they are highly profit oriented. Take high-speed broadband internet access, for example. SpaceX and Starlink want to get direct to the consumer. And they want, of course, they want to do that with a profit-oriented approach. And in the old space industry, you have a high cost of development, and hence you need high reliability and more stringent testing. And the mission life cycles tend to be very long. And the industry itself, as a result of all this, was slow to evolve. I would say the aerospace grade components, if you look at, especially in the semiconductor industry, if you look at aerospace grade components and the cutting edge commercial grade components, there's always at least 3 generations of gap between the technology they use. For example, when the commercial industry was using 28 nanometers, 28 nanometer silicon chips, the traditional old space industry would still use something like 90 nanometer semiconductor technology because they were relatively slow to evolve. Using a new component in such an environment would require a lot of testing, particularly radiation testing, to make sure they're qualified to survive long time in space, because space is a much more harsh environment where you don't have the protection like the protection from radiation that you have in Earth. So high speed particles can cause significant, what we say, significant upsets in electronic circuits in space. So because of that, you need to qualify your components, especially semiconductor components, before you use them on what we call long mission life cycles in space. But when it comes to new space applications, the primary target is low cost. So in order to achieve low cost, they are willing to sacrifice a little bit of the reliability and focus on fast deployment. So like I said earlier, use lesser grade components and have short mission life cycles. Instead of operating a satellite for 15, 20 years, unlike in traditional applications, they may probably only operate for like 5 to 10 years. And then at the end of 5 or 10 years, they'll launch another satellite to take its space and deorbit the existing satellites. And they can still do that. They can, because of the low cost. If you can develop a satellite for 1/10 of the cost of the traditional satellite, you can even replace it, like even if you replace it every 5 years, over 20 years, your accumulative cost is still lower than a traditional space industry. So this is where short mission life cycles, and also because you are able to quickly evolve, because of that, you can give more, you can use more better technologies to give better services to your consumers. And this is a must if you're operating in a profit-oriented competitive environment, in such as providing like global high-speed internet. So this is, like I said, this is the new revolution that is happening in the satellite industry right now. And as I said earlier, old space industry constellations will rely on low number of satellites per constellation, whereas in the new space industry, you have a large number of satellites, thousands or tens of thousands. And of course, they rely on launching multiple satellites, like hundreds of satellites at a time. So they have to be streamlined and they have to be built to a standard where they can be stacked and put on the launcher together, and they can be launched in sequence in one go. And of course, when it comes to barrier of entry for new engineers, in the old space industry, there used to be high barriers of entry because they were driven by national governments and they were serving strategic objectives. In most cases, they were you need defense clearance for such projects. And of course, they were limited to nationals of their own countries. But in the new space industry, because they're commercial driven and they have commercial objectives, and they're less stringent on this, what we call defense or security clearance, there's less barrier of entry. And they are on the lookout for talent. They will offer competitive compensation for talents, and they are also willing to go global and go beyond national boundaries and be truly multinational. So therefore, even for anybody, any qualified engineer anywhere in the world could get better opportunities in the new space industry. And as the new space industry grows, as it is projected to grow, you can expect more and more opportunities to open up to all types of engineers, including and especially electronics engineers in the space industry. So I would say the future is bright in the space industry for electronics engineers. So the young undergraduates, such as yourselves, could brace yourselves for a career in this area if you're interested in it. So talking about a career in the space industry, so what are the demands of such a job? And I would say this is not unique to the satellite industry or the space industry. This is something which is applicable to any industry which you may go into after you graduate. So first thing you must acquire is a sound understanding of the fundamentals of electronics, and you are in the best place in Sri Lanka to get that exposure. So I would advise all of you to use all the means at your disposal to achieve this target of obtaining a sound understanding in the fundamentals of electronics. And then, of course, you will also need to develop strong practical design skills and experience. So most of your experience will come after you graduate, when you step into the industry. But even while you're still in the university, you can engage in, there are a lot of design projects that you can take part in, and also competitions. Like we used to engage a lot in electronics design competitions and robotics design competitions. So these things will give you a lot of exposure to the outside world and the outside industry, and you will gain some valuable design skills and experience which you cannot gain through other means. So you must obtain both these aspects while you are in the university as undergraduates. And of course, you need to develop strong analytical and problem solving skills. And this, I'm sure most of you in our department already possess these skills. So you just need to sharpen up these skills and make sure you stay up to date with the relevant technologies and the developments of the wider industry, so that you can stay relevant. Even in a few years' time, you can still stay relevant. And next, of course, is great teamwork. As you can imagine, in any industry, it requires great teamwork. And especially in this industry, you need to have like have a lot of cross-discipline engineers, like I said, mechanical, uh, electronics, aerospace, and I mean, even software engineers. So you need to have all these people working together towards a common goal, and you need to interact with different disciplines, and also have good communication skills to make sure that the project goes on time and on schedule and without any communication gaps. So great teamwork is always a requirement, no matter which industry you go into. And finally, the most important thing is a positive attitude. A positive attitude is always required if you're going to do challenging work, because the kind of development that I talked about earlier, but they used to be out of reach just a few years ago. But due to people pushing ahead with a positive attitude, a positive can-do attitude, most of the things that were unavailable to us, most of the opportunities that would have been unthinkable maybe 10 years ago, are within our reach today. And it is because of this kind of attitude that we are able to, push the boundaries of space, not just space, push the boundaries of technology and achieve things that were unavailable to us, that were even unthinkable to us maybe a decade ago. So I would say these are the core fundamentals. These are the pillars on which a good engineer is built upon. And I would encourage you, like I said, you're in the best place in Sri Lanka to develop these skills and knowledge. So to use all the means at your disposal to get these design skills and experience, and also use this as you be open to the rest of the world, stay relevant to what is happening, and make sure you develop the required knowledge and skills to be relevant in the industry by the time you graduate. So that would be my advice to you as budding young engineers. So with that, uh, I bring my formal presentation to the end. So thank you very much for all of you for joining me, and thank you for inviting me to deliver this talk. I hope I was able to motivate the young undergraduates to become world-class engineers. And so this only brings the formal part of my presentation to an end. So right now, then I will like to open up the floor for you guys. So now it's open for questions, and I would like you to raise questions and also any suggestions you might have, and to make this a very interactive discussion. So the floor is open to the audience. So over to you. Thank you.
Yes, thank you, Mr. De Silva. Dr. Ranga, would you like to say something?
Of course, yes. Very pleasant memories, Kalana. You see, I mean, you have not changed much, and I think you learned how to pack many electronics into one system using your small car also. And the elevator pitch, we never forget the elevator pitch that you did. We remember how you were punished. Someone hired you to his company and kept you with him for 4 years. And your very famous paper also, this 4K paper that became very famous, and transactions of circuits and systems of video technology paper was a beautiful thing at that time. So thank you for these great contributions and inspiring many.
Thank you, sir.
Now you reach this pinnacle of electronics in Singapore. So are there examples also in Singapore like you?
Actually, sir, when it comes to electronics, there are a lot of people here, but most people are actually studying computer science. So in the electronics industry, there aren't that many people that I know of who are like in the core electronics industry. Maybe if I can find some people, maybe I'll pass their contacts to you, sir.
So Malin went to MIT. Geethan, Manupa is in Singapore, right?
No, sir. He's now in UK. He's
In
in.
the UK.
He joined ARM after finishing his PhD. He went to UK, and now he's working in ARM.
In ARM, yeah. So
Yes.
that's electronics. Yeah, not too bad.
Yes,
Right?
that's electronics. Yes.
Yes. Geethan.
Geethan is still following his PhD. So
Yes.
he's in ETH Zurich, and he's
Zurich,
working
yeah,
in.
yeah, remember, yes, yeah.
He's working in IBM because his research is funded by IBM.
IBM.
So he's part-time working in IBM while doing his PhD.
Yes, okay. Yeah, although it sounds like gossip, it's inspirational for the undergraduates and for us also. We are thankful to Dr. Pascal also for inspiring people like you.
Yes, of course.
Yes. Thank you, Kalana.
Yeah.
Yes, and with that, we can move on to the audience questions. Yes, so the top question is, what speed do satellites communicate data?
Yes, this is a hard question to answer because it depends on the application.
Yes.
So for communication satellites, you have very high speed data communication, which can go all the way up to tens of gigabits per second. So that is, it depends again. Like I said, for satellites, we have multiple communication channels. For example, for telemetry and control, we use what we call typically we use what we call the S-band communications, which is low speed, but it has a high reliability and what we call it omnidirectional coverage. So for that type of links, the speeds are lower, typically few megabits per second, but the reliability of the link is high and it's omnidirectional. But for high-speed links where there's like gigabits per second communications, mostly used to transfer large chunks of data, like payload data or telecommunications signals. For that, you would use higher frequency bands. And for those, you require a more precise pointing of antennas towards the ground stations. No, so they're not omnidirectional. I would say there's a big range of speeds that you can achieve with satellite communications with the RF technologies available. It just depends, like the higher speed you go, the higher the frequency you use, and the higher, the more stringent the requirement or the tolerance of the pointing accuracy, and therefore higher the cost of the communication apparatus as well. So it really depends on the application that you're using, but you can go all the way up to I would say, I've seen of satellites which communicates all the way up to 80 gigabits per second with the ground, and those are also not the state of the art. So I would assume you could go like several hundred gigabits per second with the current technology.
Yes, that was very informative. Thank you. And the second one is a bit personal question. It's like asking, were you always interested in space-related designs? What motivated you to join this industry?
Yes. So the first question, the answer to the first question is yes. I was always interested in space-related designs, even when I was young, even during school days, I would say. But in reality, I didn't actually expect. When I chose to follow engineering and become an electronics engineer, I didn't actually expect to end up in this industry, to be honest. So it was kind of a what do you say, a chance meeting here in Singapore that led me down this path to get this opportunity. And when I came to my master's in Singapore, I didn't know that there was such a program existed in Singapore. A satellite program existed in Singapore. So I wasn't even when I was close to graduation in Singapore, I wasn't actually targeting the space industry in particular. But as luck would have it, I happened to make a chance encounter, and then things went from there, and they offered me a position in this company to join the Teleo satellite program. And then that's how I came into the industry. But yes, even since I was young, I was interested in space-related design. So as soon as I got this opportunity, I was always something I was always interested in. So just went for it. Yeah.
Yes, I think that's like common story for even for me, like doing astronomy and space related things as a hobby. We tend to like keep it on the back after going for undergrad. So I think
Yes.
that's a very good story for us also. And the next question is, can we build a small satellites here in Sri Lanka, at least a CubeSat or a nanosat? And what's the importance it has for a country?
Yes. So yes, when it comes to like pico satellites, like CubeSats, it is quite possible to do so in Sri Lanka. And in fact, I think you may have heard the news like a couple of years back. Some students from University of Peradeniya, in collaboration with a Japanese university, actually did a CubeSat, and they developed a CubeSat and they actually launched it into space. So that was so these kinds of opportunities are actually available for, especially in academia. You have initiatives where people offer ride sharing programs on commercial launch vehicles for research purposes at reduced costs. So if you would, especially if you collaborate with a foreign university who already have signed up for these shared shuttle runs, you can actually have maybe perhaps annual or maybe once every 2 years or so a program where you can launch a satellite. So I'll tell you one example here in NUS in Singapore, in National University of Singapore. They have such a program. I forgot what they called it, but they have I think every 4 years they have space to launch one single satellite. Not one single satellite, sorry, 3 or 4 satellites, but they have a significant what do you say payload area that is given to them. Within that area, they can fit any number of satellites they want. So with that, it's sort of a ride sharing program for launch vehicles. And with that, what they do is students who are interested in this area take up final year projects in this area. And so it's not a 1 year thing. You cannot launch it every 1 year. So over 3 or 4 years, they build and develop a satellite. So it could be 3 teams or 4 teams over 3 or 4 years that get together and develop a single satellite or multiple satellites. Most of the time, I think they have 3 or 4 in concurrent development. And then they put them together. And when it comes for the time of launch, they hand it over to the launch service provider, and then they launch them. And using that, they get data. And using that data, they can they use it for their research purposes and also for qualifying their electronics designs for applications in space. So like I said, if you're going to use, say, some of the cutting edge technologies or the latest generation of semiconductors in a CubeSat, even commercial vendors will be interested to see how these things go into space and how they behave in space. How much reliability can you obtain from such high-tech components? So these kinds of things. So even the industry is interested in obtaining this data. So something like that, if you can come up with a mutually beneficial proposal where the data that you collect is of interest to the people who actually do this in a commercial level, they might be even willing to fund your projects, because to them it makes sense. They cannot take that kind of a risk and put the latest generation of technology in their own satellites, commercial satellites, but they might be willing to fund CubeSats for research projects which use those technologies and then obtain that data. So this is an idea that maybe you guys can pursue. So I would say it would be a good initiative if Sri Lanka can also come up collaborate with international universities and come up with such a program, because it will give our engineers some much needed exposure to this industry, and it will open up opportunities for them to then follow up in their passion and perhaps make a career out of it.
Yes, thank you for that. Dr. Ranga, would you like to add something?
Add something? I'm sorry, no. I'm sorry, I turned on my mic. Okay, sorry.
All right, okay. So the next question is, what do you prescribe for a Sri Lankan electronic startup, given your journey from Sri Lanka to Singapore?
Okay. So when you say what do you prescribe, I'm assuming they're asking
Right.
like
Yes,
other type of products. So
like tips from what to look
okay,
out
tips
for.
What to look out for. Okay. So in terms of what to look out for, I would say mainly you should look for places where there is significant room for growth. So even if you look at industries which are already matured, where you have like people who are holding, like big companies who are holding their ground, it's really hard for startups to penetrate into such spaces. And not just for startups, even for a established company, we've seen like people trying to go into new spaces where there's already people who are like it's already matured, and not being able to get a foothold. So if you're, especially if you're a startup and if you're going for some kind of novel thing, make sure it's an industry where nobody has gotten a clear foothold, or nobody's holding a dominant state, so that it's an open playing field and somebody can actually go there, and whoever is there quicker with a better product can actually grow fast. So if you take this new space industry, for example, now if companies like SpaceX went into the crowded traditional uh, old space technologies, they wouldn't have been able to gain much ground. The way they gain ground is by doing something different and going to a space where nobody else has explored. Whereas if you were where the risk is high, but if you succeed, you have a chance of becoming the leader in that industry. And one example I can give you where the other approach didn't work is when Google attempted to go into the social media market using their own thing to compete with the companies like Facebook, who had Facebook and Twitter, who had already obtained the foothold in that market, and it failed. After a few years, Google had to pull back on that initiative, and even Google couldn't make it work because that was already a saturated market. That need was already served, and they couldn't really do anything radically different from what the others were doing. So you need to do something that is somewhat different and somewhat adds a significant value to the consumers, and a space where you don't have a clear winner yet, as of yet, so that you have a chance to be that winner.
Yes, thank you for that answer. And I think the next ones were already answered in the lecture, but you can answer it briefly. How many satellites are needed to create a complete network? I think it was explained. Yes.
Yeah, it was explained. So the bare minimum. So I would say typically in a practical sense, of course, theoretically you could say the bare minimum would be even with 3 satellites you can get a global coverage, but that's not from an engineering perspective, that's not a practical solution. So even operators sometimes have with I think even 12, 15 satellites, you can create a global coverage constellation. But then again, it will have severe limitations. So if you want to create a network where you want to provide high-speed global broadband internet, then that would require some order of thousands of satellites, like Starlink is doing, to provide such high-speed, high-bandwidth internet. But if you're only providing small services like maybe satellite telephone or satellite TV broadcasting, and if you're only focused on a certain region of the globe, not global coverage, then you can do it with a fewer number of satellites. So it's hard to answer this question without knowing the application. So if it's just and also for Earth observation, if you want to observe the Earth, then there are 2 things that you need to consider. One thing is you cannot observe Earth from geostationary Earth orbits, so it has to be in low Earth orbit. So because of that, when you're in low Earth orbit, the other thing is, what is your revisit rate? So the satellite is always moving relative to the Earth. In low Earth orbit, it won't be pointing at the same direction, same location at all the time. So it's gonna move relative to the location of the Earth. So then when the satellite rotates around the Earth, there's what we call a revisit time. So after a certain time, it will start to follow the same, repeat the same ground track. So based on those requirements, what is your maximum revisit rate you need? The number of satellites has to be decided. So even with one satellite, you can do Earth observation, which is something that we are doing right now. But when you have only one satellite, you're limited. Your capabilities are limited. So to do a truly global, what do you say, with a high revisit rate, do a truly global Earth coverage, you would require somewhere in the order of for Earth observation, somewhere in the order of 20 satellites to have a significant coverage of the Earth observation. So, like I said, it depends on your application, plus what are your requirements, what are the constraints of your application.
Yes, and with the time limitation, I think we'll have one more question. It's the top one now. It's another personal question. It's asking, would you say that the NUS Masters was the key factor for you joining ST Engineering? Or was it another path that you took?
Yes, I would say it was one of the key factors, because it was because of, because of my master's in NUS that I actually came to Singapore and happened to come across this opportunity. So yes, you could say NUS Masters was the closest key factor to joining ST Engineering and ending up here. But then again, everything that led up to that point, my time in Sri Lanka, the exposure I had in the electronics and telecommunication department, and then my subsequent time in Parakum Technologies and all the exposure I got there, all the things led me down this path. And all the skills and capabilities that I developed during that time is what enabled me to reach this opportunity. So I would say all of this played a key factor. And the masters at NUS was like the closest factor to it.
Yes, and keeping with the theme, I think I will just ask a question from my end. Were there any instances where you felt intimidated, or you thought that you were not skilled enough, but you did it anyway? Like, what type of risks did you take that along this path?
Oh, I mean, I would say there were plenty of instances where we felt that we were underpowered, and underwhelmed, but still, even if we were to fail, we still went ahead with it anyway. Especially when during my days in Parakum Technologies, we were a simple, small startup company, and we were competing with some global companies. Some of our products, we had to compete with global giants. And of course, we were behind. But then we were still doing something worthwhile, doing something new. And if we were successful, we knew we could actually get somewhere. So we went ahead with it anyway. So it's a matter of, you need to weigh in your options and see how much effort and how much risk you're taking, and what's the reward you're going to get, and is it worth it? And if it's worth it, you take the risk, because nothing comes without a risk. So it's only a matter of taking calculated risks and seeing if it's worth it. You can never have a risk-free approach to anything you do in life. So I would say, yes, go for it. If it's worth it, go for it.
Yes, thank you very much. And to give the formal vote of thanks, I invite our final year, Amaya Dharmasiri.
Karthik, can I ask a question?
Yes, sure.
Kalana, excellent presentation as usual. A bit of a political question actually. Regarding this broadband sort of service over satellite, do you think the regulatory barriers actually would enable, kind of smooth that sort of thing? Will the telecom regulators actually would resist, and the countries, because there are a lot of other things like security and basically, whatever the investment that operators actually have put, that they might become kind of not returning the returns that they were expecting. What do you think, like in the longer term, like the prospects of Starlink as a broadband internet service provider? I mean, definitely the difficult to reach locations, I think there is no other option. But when it comes to urban, I mean, there's a lot of talk here, because Starlink actually has, at least from what I know, TRC has initiated some discussion with Starlink. But what I felt actually was they can be heavily resisted by the operators. What do you think? I've been in the industry for for a couple of years now. What do you think of the Starlink's potential for truly a broadband service provider in the regular sense?
Yes, sir. Actually, that's one of the key concerns even a lot of people are raising, whether these companies like Starlink can go around these regulatory barriers when it comes to their operations. So one thing is like most of the operators who are already existing in the space would try to like protect their investment and try to do whatever they can to stop these new entrants from coming. That's one thing. And also there might be like, what do you say, when it comes to spectrum, sharing the spectrum, like ITU regulations and all, they have to go through a lot of regulations. So from what from the latest news I've followed at SpaceX especially, they have cleared some ITU regulations to obtain the spectrum that they need for the, they say, for the up to like a significant number of satellites to provide enough coverage for the USA. But then when it comes to going beyond the USA and covering the rest of the globe, there's still a lot of regulations that they have to go through. So it's actually hard to say. I mean, hard to predict whether they'll be able to go truly global with all the regulations governing, the global. And also the political implications of it. As we all know, like some countries may not like a US company providing broadband internet to their citizens because, of course, for one thing, they cannot censor anything. When it comes to Starlink, they won't be able to do that kind of thing. So, and it will be, the government will have less controls over it. So, like I said, there's going to be a bit of this, other than the technical difficulties, there's also going to be a lot of regulatory difficulties. But it seems, at least for the time being, they do seem to have cleared some of the regulators' barriers for large-scale deployment. So at least within the USA, we should be seeing mass-scale deployment within the coming years. But beyond that, like you said, it might eventually happen, but it might take longer than expected to actually get there. But personally, from my personal perspective, I have a feeling that most part of the world will eventually fall through, because I think everybody will understand that the benefits of opening up to this kind of a global internet service will outweigh whatever the concerns that they might have. So yeah, it's something that we have to wait and see what's going to happen.
Thank you, Kalana. Thank you. All the best.
Yeah, thank you, sir.
And I think Abhijit Naya also had a question for a quick moment.
Yeah, I'm sorry, it's a quick question. So I have been talking to the students. So the students have been asking me questions about the career and everything. Yeah. So I actually suggest them to go to the hardware companies in Sri Lanka, especially Parakum and like other hardware companies. But their concern is mainly that the hardware companies are moving more towards software these days. So they said even Parakum, like they have reduced their focus on RTL and are going to like software solutions. So is it because of the economy? And so we see that in other companies as well, where they give up a big product and go for small project-based system. So is it because of the economy? And what do you advise such students who are afraid to go into the hardware industry because of this?
Okay. So, so to answer the first question, like you said, when it comes to companies going to either hardware-based solutions or software-based solutions or anything else, it actually depends on the product. So companies are product companies. They provide products and services. So because of that, whatever the technology that we use behind them is a company. It's not what the consumers eventually see. So depends on the product. So for some products, you might need a software solution. For other products, the hardware solution might be the better. For some certain products, a hybrid solution might be the better one. So it depends on the product, because at the end of the day, like I said, whoever gives the better product is the one that wins. When the consumers are buying something, they're not gonna see whether it's hardware or software or whether it's a hybrid one. So only thing they're gonna see is what performance, what is the value I get, and based on that. So that's the mindset of product development. So when you're working back from a product, that kind of thing goes into a company. So that is why, like you said, companies who may have done things purely on hardware might be moving towards software right now. So even if you look at some things like traditional things that were used to be running on hardware, like software-defined networking kind of things, like people moving on software. And these things, the industry shifts because of the requirements from consumers. So those things, as hardware engineers, we cannot stop. So, but having said that, that shouldn't also discourage us from saying, okay, there won't be any opportunity for hardware engineers and for hardware-based products. It's just that when the technology shifts, you just have to find ways, different applications. Like, for example, I think I don't have time to go through the example, so I'll skip that. But let's just say this. Like we all know that in the olden days, there were when it comes to cameras, they used to be optical based, and certain companies that used to specialize in optical technologies like lenses and stuff used to hold the higher ground. But when digital technology came in, electronics companies, people who hold specialization in electronics, got the higher ground. Then the optical, those who specialize in optical, eventually they had to adapt or use their technology somewhere else. And people like Sony and those people who are specializing in electronics took that opportunity and got the other hand. So this is the nature of the industry. So it's not something anybody can actually change. And it's driven by consumers. So nobody holds the switch to say, okay, this is that. So all you can do is you open your eyes, look at the world, and decide two things. If you're interested more in the product, if what you want to get to is to give a product to the consumers, then you have to select the best technology which is available at the current time. And that might change from time to time when the technologies change. You choose the best technology available at the time, and then you go for the product. That is if you're looking from a product-oriented space. But if you're an engineer, you're a hardware engineer or software engineer or any kind of engineer, and you're looking at it from your own discipline space, and you want to do hardware engineering, then what you need to do is, okay, this product is moving away from us. Like, then we need to find another space to apply our specialization and gain a better hold. If you don't do that, eventually in the market, you will become irrelevant. That has happened to so many companies like, Kodak, Nokia, like people who have were once on the top and then gone down. So it's like I said, so for your question, when it comes to hardware engineers, what should they think? They should not just look at the traditional career paths available to them. So currently, in our graduates usually have traditional set of companies that they go to and then they look at, and traditional set of career paths, and hardly sometimes they don't actually look beyond that point. So anybody can actually, if you have a good idea, if you look at the rest of the world, if you think that you can fit, you have a good product idea, you can actually form startups, you can actually create enterprises. So that option is always open. And also there are other, even if you want to do overseas collaborations with US and European companies or any other companies who are willing to, bring their operations to Sri Lanka and set it up, there are opportunities for that. So these kind of things are there if you actually look for it. So I would say the onus is always on the engineers to keep looking and make sure they broaden their scope well enough so that actually they can find some kind of opportunity for whatever the field that they want to follow in. So my advice to you is don't get discouraged just because, okay, certain things are moving away from hardware towards software. Certain industries are going towards software. That doesn't mean hardware engineers will be out of opportunities. As a matter of fact, when the industry grows, there'll be more requirements for hardware engineers to cater to those requirements which are popping up elsewhere. So for this, even in the space industry, like I said, there'll be a lot of upcoming like requirements for hardware engineers. You can imagine with 10,000 plus satellite constellations coming up, what would be the requirement on that for engineers, hardware engineers. So there's always opportunity. It's just that you need to look in the right place. I hope that answered your question.
Sure, yeah, that was like really insightful. Thank you.
Yes, of course. Yeah, the important thing that I hear is don't get hung up on the same type of products and say like, if it's gone, like, nobody's going to go back to optical cameras. Even if you're like, let's say I'm a fan of optics, I cannot pull back the industry towards optics. It's gone to digital already. So what's gone is gone. Is look at new things. What are the new things that we can do with our specialization? That's where you should think. So with that, yeah.
Yes, thank you. Yes. And we can move on to the final part. Amaya Dharmasiri, would you like to?
Yes, thank you, Tarinder. So when we had the idea of formalizing this project of talks at ENTC a couple of months ago, we had a goal in mind, which was to expand the horizons of our budding engineers at ENTC by exposing them to various possibilities and global opportunities out there, and to inspire them to dream bigger and to achieve new heights with the specializations and the curriculum that we learn here at ENTC. So I think I speak for everybody when I say that today, after just 1.5 hours that we spend with Mr. Kalana De Silva, the goals of talks at ENTC is achieved to a great extent. And on behalf of the organizing committee, the Electronic Club and the department, I would like to extend my sincere gratitude to Mr. Kalana De Silva for finding time to give back to ENTC where you came from. And I think staying true to your roots, roots is one of those qualities that makes you a great engineer. And thank you very much for inspiring a lot of us by talking about the applications of electronic engineering in satellite system design and the nature and the trends of industry, and especially the skills and mindset it takes to be a great engineer such as yourself. So I wish you all the best in your career, in a flourishing career, building cool things and inspiring hundreds of engineers as well. Thank you very much.
Thank you, and thank you for inviting me. And I hope, I wish you guys all the best too. And I hope you will all become world-class engineers. And one day, I'll be listening to you giving your talks as well. Thank you.
Thank you, Kalana. Thank you, Tarinder. Thank you, Amaya. Thank you, everyone.
Thank you.
Yes, and with that, we formally conclude our second session. We will forward the details of the next session and post this recorded version in our official YouTube channel. So thank you everyone for participating. And once again, thank you, Mr. Kalana De Silva, for taking the time. Thank you and have a nice day.
Thank you.